All right, hey again, AP Chemistry. So quick check number 3, this first question has a lot going on that we have to pick up on, but we could use what we know to answer this question. So a couple of things. It says calculating enthalpy from data. Something that's very important to know about enthalpy. Enthalpy, delta H, has units typically of kilojoules per mole. And if you remember where we used delta H or H before, there was this equation that is not given in your textbook. Q is equal to NH. If I rearrange, let's say I have an N and I have a Q. If I want to solve for H, Q over N is going to be equal to H. So, and Q is energy, it'll be energy in kilojoules, and N is my units in moles. So we're going to need a Q, we're going to need an N, and we're going to solve in the N to get this enthalpy of this reaction in kilojoules per mole. Now, before we did enthalpy with like a phase change, this is enthalpy that we get from like reaction and energy transfer. So I have 3 grams sample of propane. It's burned and warms to 100 grams of water from 20 degrees Celsius to 100 degrees Celsius. So I put this propane, I'm going to draw a picture on the side here. I put this propane, I'm going to say this is the propane, I put it in water, and it is able to warm up where it's giving it energy to water, and water changes in temperature from 20 to 100 degrees Celsius. So energy is being transferred from the propane to the water. So this is our system, and this is our surroundings. We mentioned that before, that water is typically the surrounding. So making a note here. And then we also need to remember that delta E of the system is equal to negative delta E of the surroundings. So whatever happens to the surroundings, the negative of that is what happens to the system. So we're going to focus on our surroundings now. So I know that water is our surroundings, and it changed in temperature. So Q for water is equal to MC delta T. And we know that the specific heat for water is 4.18 joules per grams degrees Celsius. So if I get my energy for the water, it's going to be equal to the negative energy of the system, which is the propane. Okay, so I'm going to probably take the negative of this. I'm going to take this water and negate it, and that's going to be my energy of the system, okay? Or negative Q of the water is going to be equal to the system, whatever way we do this. So we're going to make a note of that here. Whatever happens to the water, the opposite's happening to the system because the energy is coming from the system. So if I want to calculate this, I know my M for the water is 100 grams. My specific heat of the water is 4.18 joules per gram degrees Celsius, and the change in temperature of the water is 80 degrees Celsius because it goes from 20 to 100. And remember, delta T is equal to T final minus T initial. That's 100 degrees Celsius minus 20 degrees Celsius. That's 80 degrees Celsius. And so if I do this energy calculation, I get that the energy is equal to 33,440 joules. And if I want to convert that to kilojoules, 1 kilojoule is 1,000 joules. So I could divide by 1,000, I get 33.44 kilojoules. Okay? Now, making a note here that this energy went from the propane to the water, and this energy is positive, right? So negative Q of the water is going to be equal to Q of the system. So if the water's energy is positive, that means Q of the propane must be equal to negative 33.44 kilojoules. That's because delta E of the system is equal to negative delta E of the surroundings. If I wanted to show you my work in doing that, delta E of the system is equal to negative delta E of the surroundings, and the surroundings is equal to 33.44. So now I got my delta E of the system is equal to negative 33.44 kilojoules. Okay, that's a little bit sloppy over there, but you get the idea, right? So that I plug in whatever my surroundings is and I negate it. If my water was negative, that means it lost energy to the system, and that means my system would have been positive. Okay, now I know my Q. If I want to solve for my H, or my delta H of the reaction, I need my N. Well, I had 3 grams of the propane. If I want N, I need to go from grams to moles. And they already told you in the problem that the molar mass of propane is 44.09. So to go from grams to moles, you divide by the molar mass. Therefore, if I have 3 grams and I divide by 44.09 grams per mole, I will get my moles, which is equal to 0.068 moles of propane, C3H8. Now, I've shown a couple of different ways. Oops, this is kind of going out of focus, my bad. I've shown a couple of different ways to calculate moles. In general, to go from grams to moles, you divide by the molar mass. Another way, you could do dimensional analysis where you put moles on top and grams on the bottom, and then you cancel out. But just in general, if you want to do it quickly, grams divided by molar mass is equal to moles. All right, so now I have my moles, I have my energy. Q over N is going to be equal to delta H, or H in general. So negative 33.44 kilojoules divided by 0.0680 moles. I'll get my answer in kilojoules per moles, which is negative 491.8 kilojoules per mole. This is the delta H of the combustion. Okay? So this is how you would use energy transferred to or from water to solve for the energy of a reaction. What is the delta H for combustion? We said it was negative 491.8 kilojoules per mole. And what is the sign of delta H? It's negative, because we know that whatever happened to the water, the opposite in sign happened to the system, which is our combustion reaction. Okay? Now, I'm going to move on to the bottom of this, still have a little bit more time in the video. Make sure you know how to calculate enthalpy from energy transfer to water. This is going to definitely show up. If you know Q equals MC delta T and Q equals NH, you could use those both combined to figure this out. Okay? Now for heating curves, this may or may not look familiar, but we have to know what goes on. If this is a heating curve for water, and it says it's at ice at negative 30 degrees Celsius, and it goes all the way to steam at 130 degrees Celsius all the way up here. Now, if I'm ice, that means the segment of A to B is a solid, and then it reaches a certain temperature that we have to know. The temperature in which solid melts will be 0 degrees Celsius. I get melting here. After the solid goes to liquid, I have all liquid here from segment C to D, and then it reaches another temperature that's 100 degrees Celsius, and it starts to boil. And then I go from liquid to gas, and finally, E to F, I'm just as a gas. And then side note, whenever I have a change in temperature, meaning these slanted segments, I could use Q equals MC delta T to solve for energy. So any of the energy changes associated with the segment, I would use Q equals MC delta T. For my phase changes, like I mentioned in a previous video, I could use Q equals NH. Okay, so for my phase changes, there is no change in temperature, so I use Q equals NH. Okay, label the graph with solid, liquid, and gas. We did that. In which segment is boiling of the water occurring? We said boiling is DE. Where on this curve would you use the formula Q equals MC delta T? So we said A, B, and then we said C, D, and then we said E, F. Whenever there is a temperature change, I could use Q equals MC delta T. Notice the flat lines, there is no temperature change, so I cannot use Q equals MC delta T. I have to use Q equals NH. Describe what is happening to the water as you move from point B to D. Well, first, the water melts and then changes in temperature in the liquid form. Right? So at B, it melts. Once it's all completely melted, it's able to heat up into, it gets 100 degrees Celsius. Delta H of fusion would be used as the water goes from point what to what. So fusion has to do with melting or freezing, and that for water is at 0 degrees Celsius. So that's segment B to C. Okay? So use this video, the second part of this video, as a crash reminder of how we interpret heating curves. You could do the exact opposite if this was a cooling curve. The cooling curve would look exactly opposite this. It would be a steam, and then it would start condensing at 100, then it would be a liquid, and then it would start freezing at 0, and then it would go back down to whatever it would be as a solid, right? So this we would call condense. We would call this freeze, and it would still be at 0 degrees Celsius at 100 degrees Celsius. And it would be gas, liquid, solid, and the freezing would go from liquid to solid, and the condensing would go from gas to liquid. Okay? So, use this video for two different things. How to calculate the enthalpy from data, given the interaction or exchange of energy with water, and then interpreting and looking at a heating curve and how to calculate and identify what's going on in each segment of the curve. If you have any other questions or concerns, please let me know.